Very good morning, students. Good morning, all of you. So let us start with the discussion without wasting any time. Last class, what we have discussed, anyone remember?
Sir, we had to start with the free radical reaction.
Free radical reactions or substitution reactions?
Sir, it started with free radical reaction.
Yes, right. So last class, what we have discussed, students. So if you look at the addition reactions, electrophilic additions, nucleophilic additions, and free radical additions we have discussed. In the free radical addition, we have RCH double bond CH2. Like HBr addition is a very good and that is the simplest example. So free radical additions generally are less number of reactions will be there, and one such reaction is the HBr addition. After that, we can start with substitution reaction. As we have seen, alkene treated with HBr in the presence of H2O2, it form RCH single
Sir,
bond CH.
slide is not visible.
1 second. Yes, slide visible right now?
Yes, sir.
Yes, right. So RCH double bond CH2 plus HBr in the presence of H2O2, it forms RCHH CH2Br. So this is nothing but a free radical addition reaction. So what happens in this particular free radical addition, we are going to study now. Can anyone say what will be happening in the mechanistic approach? So we'll discuss the mechanism of that particular reaction and then go with the substitution reactions, nucleophilic substitution SN1, SN2, SNI. What will happen in this case, students? What is going to the first step? Like whenever you have an alkene, that alkene you have treated with the HBr in the presence of peroxide. If you go with the reaction mechanistic approach, like peroxide, you can take H2O2 or ROOR or benzoyl peroxide. Like you can consider peroxide like ROOR. That peroxide is going to be undergoing the cleavage of oxygen bond, peroxy bond, and you will be getting a radical like RO dot. Like this bond, if it is cleaved, you will be getting 2 RO dot. That RO dot will be reacting with HBr. That RO dot will be reacting with HBr. Whatever the HBr you have taken, based on the bond dissociation energy, we can say only HBr additions are going to be undergoing through anti-Markovnikov rule, not HCl, HBr, or not HCl, HF, or HI. Because HF and HCl will have stronger bonds. HI bond can be cleaved to form I dot, whereas iodine radicals will form I2 again. So RO dot will be reacting with the HBr. Now the bond cleavage will happen in such a way, such that homolytic cleavage will happen. That is H dot and Br dot will produce. So we'll get ROH and Br dot. The bromine free radical is going to be obtained. The halide free radical that is now going to be reacting with alkene CH3, CH double bond CH2. You can take the pi electron density in such a way such that one electron can be given to this carbon, the other electron can be given to other carbon, and we are treating this with Br dot. So this Br dot can be attached to this terminal carbon or the center carbon, but if it Br dot connects to the terminal carbon, then you will be getting a 2 degree free radical. CH3 CH dot CH2Br, or you can also have CH3 CH2 CH3 CHBr, CH3 CHBr, CH2 dot. So this is nothing but 2 degree free radical. 2 degree free radical or secondary free radical is nothing but 1 degree free radical or primary free radical. So which is stable and why? Why secondary free radical is more stable? Is more stable due to more number of hyperconjugated structures. Is more stable due to more number of hyperconjugations. Hyperconjugative structures. Yes or no? So 2 degree free radical is more stable due to more number of hyperconjugated structures. This more number of hyperconjugated structures, because of that more stability, because of that this 2 degree free radical CH3 CH dot CH2Br is now going to be reacting with HBr again. Yes or no? That is now going to be reacting with HBr again to form respect to H dot and Br dot. That H dot will be connected with this CH dot now to form CH3, CH2, CH2Br, which is nothing but your major product. And whatever the Br dot released, that is going to be reacting with one more molecule of alkene to continue the reaction. So this is how you can have the formation of major product. Is that clear, students?
Yes.
Yes, right. So very less number of free radical reactions are there. We will be having Woods reaction, NBS additions. So we'll discuss whenever they approach. This is an example of free radical addition reactions. Now let us go with the second set of reactions. Like after the addition reactions, electrophilic addition, nucleophilic addition, and free radical addition, we are good to start with the substitution reactions. Substitution reaction. How many types of substitution reactions we can have?
Electrophilic,
Nucleophilic substitution reactions, electrophilic substitution reactions, and free radical substitution again. Okay, these are classified into, there are mainly 3 types of substitution. Nucleophilic substitution, electrophilic substitution, and free radical substitution. What is an example of nucleophilic substitution reaction? Let us start with one by one. One by one. Nucleophilic substitution reaction. Nucleophilic substitution is again classified into 3 types. What are those 3 types? 3 types or 2 types? Nucleophilic substitution is how many is divided into how many types? 3 types. What are those? SN1, SN2, and SNI. The first one is going to be SN2, SN1, SNI. So we'll start with first one, SN2 reaction. SN2 is named as 2 stands for bimolecular, N stands for nucleophilic, S stands for substitution. Bimolecular nucleophilic substitution reaction. So bimolecular nucleophilic substitution means the molecularity is 2, order is 2. The bimolecular nucleophilic substitution, molecularity is 2, order is 2. Nucleophilic substitution, nucleophile is going to substitute at the position where you have the electrophilic carbon. So what happens in this bimolecular substitution reaction? Let us take an example and understand all the points. Let us take CH3, CH2Cl, or simply let us take CH3Cl, and you treat that with a nucleophile OH minus. OH minus can act as a nucleophile whenever it is in the aqueous media. It can be acting as a base in the alcoholic media. So I have to mention specifically OH minus is aqueous now. That means it is acting as a base. So CH3Cl means the carbon is actually connected with 3 hydrogens. The carbon is actually connected with 3 hydrogens, and the carbon chlorine bond is a polar bond. The carbon chlorine bond is a polar bond. The electron density present in the carbon chlorine bond is moving towards chlorine. Due to the movement of electron density, chlorine develops what charge? Partial negative. Carbon develops what charge? Partial positive. So OH minus, which was present in the reaction mixture, which is acting as a nucleophile, that is going to attack this particular electrophilic carbon. This is going to attack this electrophilic carbon. As soon as the attack occurs, the carbon chlorine bond leaves. So this reaction occurs in one step, and you will have this type of transition states. The OH minus is now supposed to form a new bond with carbon. Carbon has already 3 CH bonds, and the carbon chlorine bond that is supposed to be cleaved. This is nothing but a transition state. It is not a step. It is a transition state. So this transition state is penta-coordinated. Penta-coordinated because around the carbon we have 5 bonds. It seems to have 5 bonds. So penta-coordinated. And because of that penta-coordination, the carbon will have more repulsions. So it is highly unstable, and it immediately forms the product. So OH, CH3 plus Cl minus. Everyone understood this point or not? So CH3Cl plus OH minus is directly forming CH3OH plus Cl minus. That means OH minus, which was supposed to act as a nucleophile, that nucleophile is attacking the electrophilic carbon, the leaving group leaves. In the formation of CH3OH and Cl minus, you are getting a transient state which is penta coordinated. So greater the repulsions in the penta coordination, this SN2 attack will be less feasible or not. If you have a transient state which is having more repulsions, in that case the transient state is not formed. In that case SN2 is not formed. That means the alkyl halide which will experience less repulsions will only undergo SN2 greatly. Which alkyl halides will undergo less repulsions? Like methyl halides, primary, secondary and tertiary I have considered. Which alkyl halide will undergo less repulsions?
Primary.
Methyl, then primary, then secondary. So only methyl will be having great, then primary, then secondary and then tertiary. That is our rate of reaction for the SN2 attack. Now understand what is actually happening in the form of this simple animation. You have my wrist, you can imagine as a carbon atom. To that carbon atom you have one bond. This is a bond which is a leaving group, carbon chlorine bond. Like we will distinguish that with the different. So this is carbon chlorine bond, yes or no? And remaining 3 bonds are CH bonds. This is carbon chlorine bond. This carbon chlorine bond is polar bond, and remaining 3 CH bonds are there as it is. Like I have taken CH3Cl. This is your OH minus ion which is coming. OH minus ion which has a which is acting as a nucleophile that has to attack this carbon, my wrist. So it has to attack from the top as well as from the bottom. But which is feasible? Just think of it. Can it attack from the top? Because already chlorine is there. Already chlorine is there, so it cannot attack from the top. So it will, because of repulsions. So the OH minus always chooses the attack from the bottom. You may ask a question, sir, bottom also 3 hydrogens are there. In every CH bond we have electrons. So whenever the OH minus is coming from the bottom, are these electrons which are present in the CH bonds, are they repelling this OH minus or not? In the top we only have the leaving group. In the bottom we have 3 CH bonds. If I replace the CH bond with CCH3, that is CH3, CH2, Cl if I consider, CH3 is there, hydrogen, hydrogen. So whenever OH minus is coming from the bottom, the repulsion is still there, but you have to think of the scenario. Whenever OH minus is coming from the bottom, these groups are not present at those positions only, rather they move slightly like this. Yes or no? And this bond is supposed to be cleaved. It was somewhere like this bond is about to be cleaved, so it is weakened. This bond is about to be formed. So it was not the 3 CH groups are present as it is. They have been shifted slightly above to maintain repulsions, minimum repulsions. Now this is a transient state which is formed. The transient state is unstable, so Cl minus has to be lost immediately. As soon as Cl minus lost, the 3 CH bonds which were present downward earlier, they are now going to be present in this fashion. Understood this or not? Everyone got this? Yes or no? So now you will be having, earlier you have a tetrahedron in this fashion. Now you have a tetrahedron. Earlier you have a tetrahedron like this with a carbon chlorine bond here. Now the OH minus as soon as attack from the top, from the bottom, that is from the back side, the 3 CH bonds have been inverted and you get a tetrahedron in this fashion. This is also tetrahedron because the carbon is sp3 hybridized. That means what happened, students, overall the inversion of configuration occurred or not? Yes or no? So that is what you need to understand carefully. So SN2 reaction rate, first SN2 rate, you can say CH3X greater, then primary, then secondary, then tertiary, to maintain minimum repulsions. It occurs in a single step. SN2 reaction occurs in single step. So rate of the reaction is directly proportional to concentration of alkyl halide into concentration of nucleophile. That means concentration of nucleophile, if you take a nucleophile which is a very strong nucleophile, the stronger nucleophiles will have greater rate for SN2. But if you take off SN1 reaction do not depend upon the concentration of nucleophile, because the rate determining step is the formation of a carbocation. In the rate determining step, the rate is directly proportional to stability of alkyl concentration of alkyl halide only. It doesn't depend upon the concentration of nucleophile. SN2 reaction occurs in single step. Rate is directly proportional to concentration of Rx into concentration of nucleophile. So order of this reaction is 2. and molecularity is also equal to 2. Molecularity is also equal to 2. And what you can say? Complete inversion of configuration occurs, which is known as Walden inversion or umbrella inversion. Complete inversion of configuration occurs. Configuration occurs. That is Walden inversion or umbrella inversion. Umbrella inversion. And what you can take in this particular perspective, like if you take methyl halide, like methyl iodide, methyl bromide, methyl chloride, and methyl fluoride, which will have greater rate. I have taken, if I take methyl halide, primary, secondary, tertiary, methyl will be greater than primary, then secondary, then tertiary. Same type of halide I am taking. The primary alkyl halide only, but I am changing the carbon halogen bond. Fluorine is taken, then chlorine, then bromine, then iodine. Which will have greater rate?
Iodine.
Why? Rate of SN2 is directly proportional to leaving group. Okay. Leaving group tendency. Why iodine is a better leaving group?
Because of its large size.
Because of its large size, the carbon iodine bond is not going to be having greater overlapping. So Ci bond that can be cleaved easily. Very good. That means you can say Ci will be having greater rate than CBr, then CCl, then CF. After this, after the stereochemistry, rate depends upon concentration of nucleophile and alkyl halide, and rate methyl halide, then primary, secondary, tertiary, and leaving group. We have to consider solvent. Which type of solvents are actually used in SN2 reactions? Polar protic or polar aprotic? Polar protic solvent is actually using, or it is going to be stabilizing the formation of your respective SN2 attack, or polar aprotic will stabilize the SN2 attack. Polar aprotic solvents undergo, or polar aprotic solvents are used in SN2 reaction. Why? You people know about polar aprotic solvents or not? Let us understand that. So what type of solvents? We have two types of solvents: non-polar solvent, polar solvent. Polar solvent again classified in two types: polar protic, polar aprotic. Solvents are classified into two types: non-polar, like CCl4, CS2. Polar. Polar means again polar protic and polar aprotic. Polar aprotic. In a polar protic solvent, what you can say is both cation and anion are solvated. The reasons we are going to study, first write down this. Polar protic means both cation and anion are going to be solvated. Polar aprotic only cations were solvated, and anions are not solvated. Anions are not solvated due to steric repulsions. Not solvated due to electronic repulsions. Non-polar solvents. Non-polar means cations and anions both are not solvated. Neither cations nor anions are solvated. Neither cations nor anions are solvated. What is this? Let us understand. Let us understand the nucleophilicity now. So if you take a I minus, like Na I have taken, Na plus I minus, Na plus Cl minus, Na plus Br minus, like NaCl, NaBr, NaI, NaF we have taken. Let us take NaI and NaF, because extremes I am comparing, you get the idea. In a polar protic solvent, because if I minus is my nucleophile, there is no method to directly store I minus. The ions are not stored generally. We have respective source from which you can generate I minus. The NaI, sodium iodide, can be added like sodium chloride, You can have sodium iodide, which will be producing Na plus ion and I minus ion. So let us take a polar protic solvent. Okay, polar protic solvent I have taken, like water I have taken. Like this water bottle, water is a polar protic solvent. Why? Because polar protic solvent are those solvents where you have partial positive charge developed on proton, that is H plus ion. The hydrogen should have partial positive charge. So that particular solvent is said to be polar protic solvent. H2O is a polar protic solvent. Now understand this point carefully, all of you. Now I have added NaI to this particular water. I have added NaI. NaI, whenever it is added, NaI, NaCl, NaBr, what happens? Solvation occurs. So Na plus ions are separated out. I minus ions are separated out. So Na plus will be surrounded by water molecules or not? Na plus will be surrounded by water molecules. Why? Because the partial negatively charged oxygen will have electrostatic force of attraction with the positively charged Na plus. So we can say ion dipole attractions have been developed. Yes or no? So what type of attractions are going to develop? Ion dipole attractions are developed. So partial negatively charged oxygen develops attraction with the partial positively charged Na plus to form this type of solvation happening. But if you take I minus, what happens? I have taken NaF and NaI, right? I minus I have taken as well as F minus. They are surrounded by H2O molecules. They are surrounded by H2O molecules. Where the number of H2O molecules will be high?
Fluorine.
Because F minus has greater charge density, we can write down this point. Okay. Because F minus has a greater charge density, the extent of hydration is greater. The extent of hydration is high. That implies F minus is surrounded by very high number of H2O molecules. I minus is surrounded by less number of H2O molecules. That implies I minus is surrounded by less number of H2O, surrounded by very less number of H2O molecules, and hence which is a better nucleophile?
I minus.
I minus is a better nucleophile, then Br minus, then Cl minus, then F minus in polar protic solvents. That means what I can say, one point is in polar protic solvent, the I minus is a better nucleophile, then Br minus, then Cl minus, then F minus. That is one point you can understand. If you take polar aprotic solvent, exactly the order is going to be reversed. But here we have said SN1 polar aprotic solvents are used in SN2 reactions, because in SN2 reaction, the rate of SN2 reaction depends upon concentration of nucleophile. If the nucleophile is surrounded by all the H2O molecules, its nucleophilicity is decreased or not? If you
Yes.
take a polar
Yes.
aprotic solvent, in the polar aprotic solvent, there is no surrounding of solvent molecules by the nucleophile. Nucleophile is not surrounded by solid molecules. So it is a strong nucleophile, it can attack. So if we take a polar aprotic solvent, nucleophile anions are not solvated. That's what we are going to discuss further. In a polar protic, both cations and anions are solvated. Same example you take NaI, NaF in a polar aprotic, DMSO, dimethyl sulfoxide, CH3, S double bond of CH3, DMSO or dimethyl sulfoxide is polar aprotic solvent. So you are not getting a partial positive charge on hydrogen. So in that case, what you can say, Na plus is going to be surrounded. Na plus will be surrounded by partial negatively charged oxygen, partial positively charged sulfur. Oxygen will be having partial negatively charged. So that is surrounded by Na plus. In a polar aprotic solvent, anions are not solvated. Anions are not solvated due to electronic repulsions. That means which is a better nucleophile now? I minus, F minus. When you compare, earlier we have compared with respect to charge density. Charge density of F minus is high because F minus surrounded by, because of that F minus surrounded by very high number of H2O molecules. But now there is no surrounding by solvent molecules. F minus, Cl minus, Br minus, I minus, if you compare, which has a greater charge density? F minus. So which is a better nucleophile?
F minus.
F minus, because there is no surrounding by solvent molecules. So F minus, which has higher charge density will be a better nucleophile. So order of nucleophilicity will be F minus greater than Cl minus greater than Br minus greater than I minus. So this is the order of nucleophilicity of halide ions in the respective polar aprotic solvent. In the polar aprotic solvents, anions are not solvated. Because of that, SN2 reaction is feasible because nucleophilicity will be high. Understood now?
Yes,
Yes.
sir.
And non-polar solvent means there is no solvation of cation or anions. So that is how you can understand. This is all about your SN2 attack. So let us look at different examples as well. Example: reaction of alcohol with PCl5 and PCl3. Can I take that example in the SN2 attack? We can take many reactions, simple reactions also I can consider. I can take CH3, CH2, Cl and treat this with NaCN. Na plus Cn minus. The Cn minus can attack this particular carbon chlorine bond leaves, generating CH3, CH2, Cn. SN2 attack. SN2 attack, no rearrangements possible because carbocation is not the intermediate. If you take CH3, CH2, Cl or CH3, CH2I and treat this with a aqueous KOH. OH minus acts as a nucleophile. CH3, CH2OH will form SN2 attack. Example, let us consider. Let us take alcohol CH3, CH2OH. Treat this with PCl5. What type of product is obtained? Alcohol treated with PCl5 produces what?
Ether.
Ether.
Sorry, ethyl chloride.
Chloride.
Ethyl chloride and
Ethyl chloride. H3P.
H3PO4. Huh? So let us look at. So if you don't know, what do you do? If you don't know what is the product, you will write the mechanism. Yes or no? So first CH3, CH2OH is there. Alcohol, ethyl alcohol treated with PCl5. PCl5 can act as an electrophile or nucleophile, or it cannot act as an electrophile or nucleophile. PCl5 acts as what? Electrophiles means I have given conditions. What are the conditions? Positively charged species with an incomplete octet. Neutral species with an incomplete octet. Octet complete species or more than octet complete species with the valence with the vacant orbitals. PCl5 has vacant orbital or not? Try to write the electronic configuration for chlorine, for phosphorus. We have 1s2, 2s2, 2p6, 3s2, 3p3. If you write the excited state, 3s1, 3p3, 3d1. But in the 3d subshell, we have 5d orbitals. Only 1d orbital got the electron. The remaining 4d orbitals are vacant. Yes or no? Phosphorus, if you try to write the electronic configuration in the excited state, 1s2, 2s2, 2p6, 3s1, 3p3 and 3d1. Yes or no? In the 3d we have vacant orbitals. In phosphorus, in 3d subshell, vacant orbitals are available. In phosphorus, in 3d subshell, vacant orbitals are available. Because of the presence of vacant orbitals, the PCl5 can act as electrophile. So let us look at the mechanism now. CH3, CH2OH, alcohol can act as a nucleophile or not?
Yes.
Alcohol can act as a nucleophile because there is the presence of lone pair of electron and oxygen. The lone pair of electron and oxygen that will be attacking this phosphorus. As soon as the attack occurs, the phosphorus chlorine bond is going to be lost. So we'll be having loss of chloride ion. So loss of this minus indicates chloride is lost. Cl minus indicates chloride ion. This minus indicates it is lost. Lost means not from the reaction mixture. This phosphorus chlorine bond is broken. So we'll have now what? CH3, CH2. Oxygen we have 2 lone pairs earlier. Now oxygen will have only 1 lone pair. It will have a positive charge. OH bond is going to be as it is, and oxygen is connected with phosphorus. Phosphorus connected with 4 chlorines now. Phosphorus connected with 4 chlorines now. Now we have Cl minus which is present in the reaction mixture. The Cl minus which was present in the reaction mixture, if you look carefully, the carbon oxygen bond and oxygen possess positive charge. Can I say the CO electron density is moving towards oxygen? Will the CO electron density move towards oxygen or not? Because oxygen possesses a positive charge, the CO electron density moves towards oxygen, developing partial positive charge on this particular carbon. So Cl minus will now go and attack this particular carbon in the SN2 manner. As soon as the attack occurs, will generate Cl, CH2, CH3. Along with that, the CO electron density is going to be given to oxygen, generating phosphorus, oxygen single bond, and oxygen regain its lone pair. So oxygen will have 2 lone pairs now, and POH bond. Along with that, phosphorus has 4 phosphorus chlorine bonds. And Cl minus picks up the proton. Cl minus attacks this particular carbon to form CH3, CH2, Cl. Now can I say POH and PCl4? If you look at this PO single bond and oxygen possessing lone pair of electron, the phosphorus double bond oxygen is a very strong bond. So lone pair of electrons and oxygen comes into. So phosphorus will now form a double bond with oxygen. Oxygen has 2 lone pairs earlier. Now it will have only 1 lone pair. OH bond you can write as it is. Oxygen's electron density has been shared now, so it will have a positive charge. Phosphorus is also connected with 4 phosphorus chlorine bonds, but as soon as the electron density comes into, the Cl minus should be lost. One of the chloride ion should be lost because phosphorus have 5 bonds around itself. So loss of chloride ion can be seen. So that chloride ion which is lost, that can pick up the proton or not, because oxygen possesses positive charge. OH electron density is moving towards oxygen. Cl minus can easily pick up this proton, forming HCl. Along with that HCl, we form P double bond O, Cl, Cl, and Cl, which is nothing but POCl3. So POCl3 and HCl and CH3, CH2Cl, these are the products. CH3, CH2Cl, POCl3 plus HCl. And what is the example? This comes under the example of SN2 attack of chloride ion to this particular alcohol to form alkyl halide. Everyone understood, students?
Yes.
Yes.
Yes, yes.
Or no? This was a mechanistic approach where you can produce the respective alkyl halide with the help of alcohols. Whenever we are looking at that reaction, this is the same reaction we are going to study twice again. So there you have to answer only, because this will be an example of reaction of alcohols and is an example of preparation of alkyl halide. Yes or no? In the preparation of alkyl halide, we look at the same reaction. In the reactions of alcohols also, we look the same reaction. Next reaction with PCl3. Same type of reaction with PCl3. So I take CH3, CH2, OH. We have lone pair of electrons on alcohol, and we are treating this with PCl3. So we have phosphorus has vacant orbitals, lone pair of electrons and oxygen can attack the phosphorus. As soon as the attack occurs, the phosphorus chlorine bond leaves. So loss of chloride ion occurs. So it generates what? CH3, CH2. Oxygen has only 1 lone pair. Other lone pair involved in the new bond formation, oxygen phosphorus bond. Phosphorus has 2 chlorines now, and the chloride ion is lost. The chloride ion which is lost in the previous step, that is now go and attack. That will now go and attack the electrophilic carbon, because this carbon is connected to oxygen which bears positive charge. This carbon is connected to oxygen which bears positive charge. So Cl minus attacks from the backside. So what is this attack called as SN1 and SN2?
SN2.
SN2 attack occurs. The carbon oxygen bond is going to be cleaved to neutralize that positive charge. You will generate what? CH3, CH2Cl plus POH. Oxygen regain its lone pair, and we have 2 phosphorus chlorine bonds as well. POH, PCl, whatever it is there, that is going to again react with 1 more molecule of alcohol. This is first molecule of alcohol. First molecule, second molecule of alcohol I'll take now. CH3, CH2OH plus POH, Cl and Cl. Lone pair of electrons and oxygen attack the phosphorus. As soon as the attack occurs, what happens? You will form CH3, CH2, oxygen OH bond is going to be present. One lone pair and a positive charge on oxygen. Oxygen connected with phosphorus, which is connected to OH. And as soon as this attack occurs, chloride ion is lost. So we have only one phosphorus chlorine bond now, and the chloride ion is lost from this molecule. So Cl minus, which is lost, that is now going to attack this particular electrophilic carbon from the back side. This carbon is electrophilic. So SN2 attack happened again. So Cl minus attack, you generate CH3, CH2Cl. Along with that, we generate POH, OH and PCl. Again, we have phosphorus chlorine bond or not? So that can again react with the third molecule of alcohol. So let us take the third molecule of alcohol, CH3, CH2OH. The third molecule of alcohol can react with a POH, POH, PCl. Lone pair of electrons and oxygen coming and attacking the phosphorus. Phosphorus chlorine bond leaves. Loss of chloride ion. Generate CH3, CH2. Oxygen will have only one lone pair, positive charge. OH bond as it is. Oxygen connected to phosphorus. Phosphorus connected to OH groups. Cl minus, which is lost in the previous step, that will attack this carbon, electrophilic carbon again, generating CH3, CH2, Cl. Along with that, we produce what? POH, OH, OH, which is nothing but H3PO3. So I can write the total reaction of 3 molecules of alcohol, 3 molecules of CH3, CH2OH reacted with PCl3, 1 molecule of PCl3 to form 3 molecule of alkyl halide CH3, CH2Cl plus H3PO3. Yes or no? This is a reaction or not? CH3 molecules of alcohol, 3 molecules of CH3, CH2OH react with 1 molecule of PCl3 to form 3 molecules of alkyl halide and 1 molecule of H3PO3. In the place of molecule, you can write moles. 3 moles of alcohol will react with 1 mole of PCl3 to form 3 moles of alkyl halide and 1 mole of H3PO3. Is that clear? In all the cases, SN2 attack is happening. So this attack of PCl3 and PCl5 with the reaction of PCl3 and PCl5 with alcohols to form respective alkyl halide is an example of SN2 reaction. And in the case of PCl5, you get POCl3 and HCl. In the case of PCl3, you get a H3PO3 as a side product. Is everything clear, students, so far?
Yes, sir.
Yes.
No doubts, right? So what is the doubt I have is, we have PCl3. Earlier we have taken PCl5, not an issue because phosphorus do not have a lone pair of electron, it has only vacant orbitals. In PCl3, phosphorus do possess a lone pair of electron. Along with that, it also has a vacant orbitals. PCl3 means what? Phosphorus should have 5 electrons around itself. So the 2 electrons are present. 2 electrons are present as a lone pair and 3 phosphorus chlorine bonds. And phosphorus also has a vacant orbitals. Phosphorus also has vacant orbitals. 3 phosphorus chlorine bonds are there. So the phosphorus here can act as a nucleophile or not, because it is a species. Around phosphorus, we have 3 phosphorus chlorine bonds and 1 lone pair, 8 electrons are there. Neutral species with complete octet can act as nucleophiles. Why can't the PCl3 act as a nucleophile and attack this particular electrophilic carbon? Because alcohols also has partial positive charge here. Why can't the lone pair of electron phosphorus attack this carbon? That is the first doubt. And the second doubt what we have is, sir, you are saying chloride ion is lost. Chloride ion which is lost, that is attacking the electrophilic carbon from the backside. Why can't the chloride ion will go and pick up this proton? Because oxygen possesses a positive charge. Oxygen is also connected with carbon. Oxygen also connected with hydrogen. The OH electron density is also moving towards oxygen, developing partial positive on hydrogen. Why can't Cl minus act as a base and pick up the proton to form HCl? This is the second question which you should ask yourself. What are the answers? Anyone? In both the questions, the answer is same. The answer is going to be like this, like the chloride ion is going to attack from the backside and the CO bond is leaved because the phosphorus POH PCl4, that is a very good leaving group. Why? Because that will ultimately lead to the formation of P double bond O. P double bond O is a stronger bond. P double bond O is a very strong bond. Because P double bond is a very strong bond, the CO bond is going to be cleaved. Because of that only you are getting this POCl3. Understood this point? That is why only chloride ion is attacking the electrophilic carbon, not the proton. It can also attack this particular H plus. If you think of that, that is not happening. The chloride ion is not picking up the proton, but if you think of the reaction of SOCl2, chloride ion picks up the proton. That is a different case. That is SNI reaction. We'll discuss that. The chloride ion is not picking up the proton because the POH will ultimately lead to the formation of P double bond, which is a very strong bond. So this total group is a very good leaving group. Since this total group is a very good leaving group, you are having not the nucleophilic attack of phosphorus. Phosphorus lone pair cannot act as a nucleophile. Rather, the electrophilic attack is going to happen, which will ultimately generate the phosphorus oxygen bond. Yes or no? Why can't the PCl3 act as a nucleophile even though it possesses a lone pair of electron? Means because if alcohol acts as a nucleophile, there is a formation of PO bonds. Because of that, P double bond can be formed if I try to write the resonance structure. Because of that, it will be more stabilized. And these groups POHCl2, they are better leaving groups because P double bond is stronger. Right, students? So these are the reactions of alcohol with PCl3 and PCl5, which are SN2. So let us go with the next set of reaction, like SN1 reaction. SN1 reaction, what is SN1 reaction? SN1 is unimolecular nucleophilic substitution.
Substitution reaction.
Nucleophilic substitution. See, understand the mechanistic approaches, whatever I'm saying. Initial days, you might be feeling some difficulty. I do agree. There might be some students who have studied only the reaction like substrate and products. What happens? That's okay. But try to develop understanding regarding the mechanistic approach, because that will give you complete clarity of what they are asking and what type of product you will get and all. You won't feel any burden once you go with this type of study. So SN1 reaction, it is a two-step reaction. First thing, it is a two-step reaction. Formation of carbocation, the alkyl halide, the slow ionization of CX bond or carbon leaving group bond to form a carbocation is the rate determining step. The slow ionization of Cl, what is L stands for? Leaving group. The slow ionization of Cl bond to form carbocation is the rate determining step. And carbocations are formed, so rearrangements are possible. Rearrangements are possible. So what type of carbocation is more stable? So rate, if you try to compare rate CH3X, primary, secondary, tertiary, which will have higher rate? Tertiary, because obviously tertiary carbocation is more stable due to more number of hyperconjugated structures. Leaving group, in the carbon leaving group, better the leaving group, obviously you will have greater rate for SN1 as well. So Ci bond, CBr, CCl and CF. So this is the same order even for SN2 as well as SN1, because good is a better is a leaving group, greater will be the rate. And also kinetics. Kinetics, if you study, rate is directly proportional to concentration of substrate only. So rate of the reaction is rate of SN1. Rate of SN1 is not dependent upon, is independent upon concentration of nucleophile. Rate of SN1 is independent upon concentration of nucleophile. That is the kinetics. So order is equals to 1. Molecularity of this reaction is also equal to 1. And what type of solvent is useful? Polar protic or polar aprotic?
Polar protic.
Why? Polar protic solvent is useful in SN1 reactions. Why, students? Because what I'm saying, if I take CH3, 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 Cl, what happens in the first step? Example, if you take CH3, 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 Cl, and I'm treating with OH minus aqueous. In the presence of aqueous medium, OH minus acts as a nucleophile. So step 1 is going to be breaking of carbon-chlorine bond. So the carbon-chlorine bond is going to be cleaved slowly to form a respective carbocation. CH3, CH3 plus CH3. This is first step. Step 1. Step 2 is what? Step 2 is CH3, CH3 plus, because it is a most stable carbocation. It is going to be attacked by the nucleophile fastly, forming respective alcohol CH3, CH3, OH. It is a slow step. So that is why rate determining step. Fast attack of nucleophile. So why we are saying polar aprotic solvent is useful in SN2? Why? Because in SN2, if you have a polar aprotic solvent, the polar aprotic solvent cannot solvate the anions. So if anions are not solvated, greater will be the strength of nucleophile. So greater is the strength of nucleophile, greater will be the attack. Because the rate of the SN2 reaction will depend upon concentration of the nucleophile. But SN1 reaction rate do not depend upon concentration of nucleophile. And we are saying polar protic solvent. In the polar protic solvent, cations and anions both are solvated. Cations are solvated in polar aprotic also. That means what is the cation obtained here in the rate determining step? Carbocation is obtained. Carbocation is a cation. Yes or no? It is a positively charged species. So that positively charged carbocation can be stabilized not only in polar protic but also in polar aprotic, because cations are stabilized in both the cases. So why again I am taking polar protic only? Are you understanding the question? Carbon chlorine bond, if we cleave the carbon chlorine bond, you will generate respective carbocation. That respective carbocation can develop attraction with a polar protic solvent or polar aprotic solvent also, not an issue. Because polar aprotic solvent also solvate the cations, not the anions. But why again we are saying polar protic? Because if you look at the carbon chlorine bond, understand this point carefully. In the carbon chlorine bond, you have partial positive, partial negative, right? In the carbon chlorine bond, you have partial positive on the carbon and partial negative on the chlorine. Look at this attack. The partial positively charged carbon will be solvated by, the partial negatively charged chlorine is also going to be solvated. Solvation is nothing but we are not having carbon chlorine bond completely cleaved and then only solvent molecules come. That is not the scenario. The scenario is the carbon chlorine bond, whatever it is there, slowly the solvent molecules will come and develop new interactions. Because of the new interaction, this bond is going to be cleaved. So Cl minus is an anion which is solvated, which is again solvated. When it is solvated, if you take polar protic solvent only, because Cl minus is also solvated and carbon with the positive charge is also solvated, the carbon chlorine bond is going to be cleaved. Because of polar protic solvent, the ionization of carbon chlorine bond will be happening fastly. Are you understanding this point or not?
Yes.
Because of polar protic solvent, the polar protic solvent will ionize the carbon chlorine form to form the cation. Polar protic solvent is useful in SN1 reaction as it will ionize the substrates to form carbocation, or you can say it helps in bond cleavage. Whatever the bond cleavage you are having, that is going to be helped by the polar protic solvent. So polar protic solvent means SN1, polar aprotic means SN2. So that is how you have to understand. So SN1 and SN2 reactions. SN1 reaction is a two-step reaction. The slow ionization of carbon leaving group to form a carbocation. Carbocation formed means rearrangements are possible. Rate will be greater for 3 degree, then 2 degree, then 1 degree, then methyl halide. Rate will be greater if you have a better leaving group. Yes or no? All these points are clear to everyone or not? These are very interesting
Yes.
points to understand, students. You can just go with all these points and do different types of questions. Example, we can take. I will be taking this type of alcohol. This type of alkyl halide, let us say. Treat this with H2O. What you will get? What type of alkyl halide? What type of alkyl halide? Secondary or tertiary? Let us take CH2CH3. Let us take CH2Cl. So it is what type of alkyl halide? Carbon connected with only one of the carbon atom. It is a primary alkyl halide. So the mechanism goes like this: first formation of the carbocation, then the ring expansion. Because carbocation, when it is formed, ring expansions and rearrangements are possible. So CH2Cl will undergo loss of carbon chlorine bond. So loss of chloride will happen to form respective CH3 here and a CH2 plus. Try to give numbering 1, 2, 3, 4, 5, 6. Not the IUPAC numbering. The numbering has been given just to form a 6-member ring. So 2-3 bond or 2-6 bond you can cleave because ring expansion is not the rate determining step. So I'm cleaving 2-3 bond. So first and third were now connected. First connected with second, second to 6, 6 to 5th, 5th to 4th. And also second is connected to which substitutions? Second is connected to methyl group. Methyl group. First is not having any substitution. Now where do we have the positive charge?
Second.
Second carbon, because that has seen the net loss in electron density. Very good. What type of carbocation is this? It is already 3-degree carbocation, which is more stable carbocation. So now what happens? H2O comes into picture. H2O acts as a nucleophile. Lone pair of electrons present on oxygen. So the lone pair of electrons on oxygen will attack this particular carbon to form what? CH3. Oxygen used its lone pair. So one lone pair will present on oxygen, 2 OH bonds and a positive charge on oxygen. So ultimately in the final step, loss of H plus will occur to form respective alcohol in this fashion. This is a major product. Everyone got this reaction, students? Yes or no?
Yes, sir.
Sir, why does SN1 not dependent upon the nucleophile?
Why? SN1?
Does not depend on the concentration of nucleophile.
You only answer. I have given these 2 steps as the reaction mechanism. Which is the rate determining step?
Formation of carbocation.
In the formation of carbocation, what is the substrate present? Step 1 is this one, right? CH3C, CH3, CH3Cl, giving respect to carbocation. This is a slow step, rate determining step. In the rate determining step, rate of this particular reaction should be directly proportional to concentration of substrate present. Reactants. What is the reactant in this particular step? Only alkyl halide. There is no nucleophile in the rate determining step.
Okay, sir.
Okay, understood. So rate determining step, from the chemical kinetics, what we know? The rate of a reaction is directly proportional to product of concentration of the species present in the rate determining step. What is the rate determining step? Formation of carbocation. In the rate determining step, we only have alkyl halide. We do not have nucleophile at all. So rate should be directly proportional to only concentration of alkyl halide or substrate, not depending upon concentration of nucleophile. Okay?
Okay, sir.
Okay, fine. So next example, we try to do what happens here. Let us give a 4-member ring. What is the major product? Try to solve, all of you. What is the major product in this particular reaction? You can answer very simple. Okay, what happens in the first step?
Cl minus Ds.
Then after that, Is
Ring
ring
exp-
expansion possible? So we can have this type of product. Carbon chlorine bond is going to be lost. Loss of chloride to form a respective carbocation. So this carbocation can undergo ring expansion. So I can say 1, 2, 3, 4, 5. So 5-member ring is going to be formed. So 2, 3 bond I am cleaving, and 1 and 3 connection is there. 1 is connected to 2, 2 connected to 5, 5 connected to 4. And which carbon has substitution? First carbon, what substitution? Methyl. First carbon seen the net loss in net gain in electron density. So positive charge on first carbon is lost. Third carbon, no loss, no gain. Second carbon has seen the net loss. So second carbon will have a positive charge. What type of carbocation is this? 2-degree carbocation. You can do 1, 2
Second.
hydrate shift. We can do 1, 2 hydrate shift. If 1, 2 hydrate shift occur, you can generate a 3-degree carbocation. 3-degree carbocation is more stable. Now what will happen? Last step. Now what will happen is, last reaction and this reaction, everything same. Just I have mentioned this heating. What happens whenever you do the same treatment of alkyl halide with H2O in the presence of high temperature heating? Okay, elimination occurs. Elimination I have not discussed, but whenever you have given the weak nucleophiles have a greater tendency to undergo SN1, weak bases at high temperature will have a tendency to undergo E1. So because of high temperature, elimination involves bond cleavages. So here what happens is, H2O is now going to act as a base. It tries to pick up the proton from this particular carbon. CH electron density comes into, you will generate this particular product major. You can write down on one point. At high temperature, elimination occurs. That means I am doing the hydrolysis reaction only, but not at normal temperature. If they have mentioned temperature condition, you have to do elimination. Why elimination will be happening at high temperature? Because elimination involves cleavage of bonds. If temperature condition is not mentioned, substitution occurs. So there is always a competition between SN1, SN2, E1, E2. We are going to study the comparative study for SN1 occurs or SN2 occurs or E1 occurs or E2 occurs for different types of alkyl halides in your alkyl halides chapter. Just I have given this example so that you can understand. If you have found an alkyl halide treated with H2O, you cannot do directly SN1 because temperature condition mentioned. So you have to do E1 elimination. E1 and SN1 involves the formation of carbocation. So they are happening at polar protic solvents. The polar protic solvents are useful to do SN1 or E1, and SN1, E1 do not depend upon the E1 means we have to talk of base. So weak bases and weak nucleophiles, they are useful in SN1 and E1. SN1 means weak nucleophile you have to consider. If you have a strong nucleophile, because rate of SN2 depends upon concentration of nucleophile, so strong nucleophile will undergo SN2, it won't undergo SN1. If you have strong base will undergo E2, it won't undergo E1. Okay, we'll discuss all the comparative study, but I have just explained as we approach an example. So this is about SN1, SN2 reaction, students. Then we undergo SNI reaction. SNI means internal nucleophilic substitution. The best example of this particular SNI is reaction of alkyl halide, reaction of alcohol with thionyl chloride to form respective alkyl halide. The reaction of alcohol, the reaction of ROH with SOCl2 to form alkyl halide. Alkyl halide proceeds through SNI, that is internal nucleophilic substitution. And one more point you have to understand in SN1. In SN2 we have looked the stereochemistry. In SN1, what is the stereochemistry? I have explained this while explaining racemization. How many of you remembered? partial racemization occurs. Partial racemization occurs in SN1 as partial racemization occurs in SN1. Why? Partial racemization occurs in SN1 as the leaving group lost cannot diffuse greatly. As the leaving group lost cannot diffuse greatly. You can understand this particular point again by drawing a tetrahedral. Initially, we have an alkyl halide where the carbon chlorine bond was like this, and the three carbon, like carbon chlorine bond is a leaving group. Initially, the leaving group has to lost, but this loss mean it is this bond is broken, but that does not mean the Cl minus has been removed from the reaction mixture. It's a this Cl minus which is lost, that will be moving here only. Its concentration is still present here. As soon as it is formed, we form a carbocation. So carbocation will have a trigonal planar. So we got planarity. So nucleophile can attack from the top as well as from the bottom. But from the top, attack is slightly less. Why? Because still the leaving group concentration is present. So it will attack from the bottom. So you can say partial racemization occurs as the leaving group lost cannot diffuse greatly away from the carbocation carbon. SN2, what happens? Walden inversion, SN1, partial racemization. SNI, what happens? We'll study. SNI reaction, this is the best way to prepare alkyl halide if you remember. Alkyl halide ROH plus SOCl2 will be forming respective RCl plus HCl plus SO2. It is the best method to prepare alkyl halide. Why?
Because HCl and SO2 both are gases.
Yes. If they are gases, what is the reason?
They lost
Is it-
easily, sir.
They are lost easily, or we can also say thermodynamically. Thermodynamically, whatever the reaction which is increasing the entropy of the system. If a reaction increases the entropy, gases are actually having more randomness. We can apply the concept of thermodynamics. The reaction which is actually producing gases, which is increasing entropy, is more feasible. Okay. This is the best method to prepare. This is the best method to prepare alkyl halide. Alkyl halides as HCl and SO2 are gases which increases entropy of the system, which increases the entropy of the system. They can also be removed easily. Entropy of the system, and they can also be removed easily. SNI is nothing but internal nucleophilic substitution. The reaction of alcohol with SOCl2 to form alkyl halides proceeds through SNI. So let us look at the mechanistic approach now. ROH, let us consider CH3, CH2OH. CH3, CH2OH plus SOCl2. SOCl2 will have S double bond O Cl, Cl. So can I say SOCl2 will also act as an electrophile? Like PCl3 and PCl5, SOCl2 will also act as electrophile. Why? Because S double bond of pi electron density is moving towards oxygen. The S double bond of pi electron density is moving towards oxygen, and you can also say chlorine is also more electronegative when compared to sulfur. But pi electron density movement is great, so that is why lone pair of electron attack the sulfur. Pi electron density moves away. So you can write CH3, CH2. Oxygen will have only one lone pair now. Oxygen has a positive charge, OH bond as it is, and oxygen will have a sulfur. Sulfur now connected with SO minus, Cl, SCl. SCl, SCl. So negative charge on oxygen comes into, because S double bond is stronger. As soon as negative charge comes into, chloride lost. Loss of chloride occurs. So you can have CH3, CH2, oxygen having one lone pair, positive charge, OH bond, and oxygen connected with S double bond O, S double bond and Cl. Whatever the chloride which is lost in the previous step, that will attack this particular carbon or not. Now understand this point carefully, students, all of you. The chloride which is lost in the previous step, earlier if you look at the PCl3, PCl5 attack, I have attacked the chloride to this particular carbon saying it is SN2. If I do the same attack now, it has to be SN2. But a chloride will not attack in this manner. Rather, what happens? The Cl minus ion, which is present in the reaction mixture, that picks up the proton. The OH electron density is given to oxygen to form CH3, CH2O. So to form compound like this. You may ask a question, sir, why? How do you decide whether it is attacking the electrophilic carbon or it is going to be attacking the hydrogen? Why, students? Cl minus picks up the proton, so we can say HCl is formed here. Cl minus earlier attacked the electrophilic carbon. Why? What was the reason there? I have told you the reason, right?
Forms the better.
Better leaving group, because PO bond is going to be formed, which ultimately forms P double bond O. That is a better leaving group. But now I'm not saying that Cl minus attacking the electrophilic carbon, because Cl minus picks up the proton, and as soon as the proton is picked up, the chloride ion is now going to internally attack this particular carbon, releasing out SO2 gas. Releasing out SO2 gas in this fashion. So it's not like a S double bond O SOH Cl is formed. That will not happen. Rather, chloride picks up the proton, Cl minus attacks the carbon, S double bond O leaves. This is nothing but this step is actually internal nucleophilic attack. That is why the name internal nucleophilic substitution. Internal nucleophilic attack occurs. Nucleophilic attack. As soon as the internal nucleophilic attack occurs, we get CH3, CH2, Cl, and S double bond O is obtained. SO2 is a gas which is increasing entropy. CH3, CH2, Cl plus SO2 plus HCl is also obtained in the previous step. So those are all the side products, and alkyl halides are the main products. Is that clear? So since the internal nucleophilic substitution occurred, can I say what is the stereochemistry of the product? Inversion occurred or racemation occurred? Can I say inversion occurred? Can I say like that? Is the nucleophile attacking from the backside? The nucleophile is not attacking from the backside, so inversion did not occur. The nucleophile is not attacking from top and bottom. Decimation did not occur. Nucleophile is just substituting the carbon where earlier you have OH group in the same direction. So the configuration was not changed, so retention happens. Retention of configuration. Retention of configuration is observed in the case of SNI attack. Retention of configuration is observed in SNI attack. SNI attack. Retention means no change in configuration. No change in the configuration. Retention means there was no change in the configuration. Got it, everyone?
Yes, sir.
So simple. SN2 inversion occurs. SN1 partial decimation. SNI retention will happen. So this is how you can understand this reaction. Now do this reaction. Write down the product. CH3, CH2, CH2, Cl, or CH3, CH2. Okay, CH3, CH2, CH2, Cl treated with SOCl2 in the presence of PY produced A. Example. In this reaction, what happened? Retention, inversion, partial decimation. In this reaction, what happened to the stereochemistry? What happened to the stereochemistry of the product? A, inversion. B, racemization. So whenever partial racemization is not given, you can go with the racemization. C, retention, and D, none. D, I can say both A and B, both A and C. Answer this question. So everything is fine, right? Only thing I have added is PY. What is PY?
Pyridine.
Pyridine. So what happens if I add pyridine? Earlier, if I don't give pyridine, you should directly go retention. If I don't give pyridine, you can directly attack in this manner, generating CH3COH with the positive charge on oxygen, S double bond of Cl. Cl minus picks up the proton, internal nucleophilic attack, retention, you can write down. But if I add pyridine, what the mistake happened, or what is the change happened? So let us look at the mechanistic approach. What is the mechanistic approach? So we have CH3, CH2, CH2Cl treated with SOCl2, CH3, CH2, CH2Cl. SOCl2 is S double bond of Cl and Cl. So I can, this is alkyl, this should be alcohol, right? CH3, CH2, CH2OH. Okay. Lone pair of electrons on oxygen attacking sulfur, generating CH3, CH2, CH2. Oxygen, only one lone pair now, positive charge, OH bond, S, O minus, Cl and Cl. The negative charge on oxygen comes into, chloride ion is lost. So whatever the chloride ion lost, the chloride ion is lost, and you will get CH3, CH2, CH2. Oxygen will have one lone pair, OH bond, positive charge, and oxygen connected to sulfur, sulfur connected with the S double bond O and Cl. Now what should happen? Earlier what we have done? Once we get this product CH3, CH2, OH with the positive charge on oxygen, S double bond O, Cl, the chloride ion which was lost in the previous step, that picks up the proton. But now we have pyridine or not? Pyridine is an acid or base?
Base.
Pyridine is a base. Can I say pyridine now picks up the proton? The chloride ion is not supposed to pick up the proton. Rather, pyridine will pick up the proton now. Pyridine will pick up the proton to form a pyridinium chloride. So what will happen now is you get CH3, CH2, CH2. Oxygen will regain its lone pair. OH electron density is given to oxygen, and you will form S double bond of Cl. So along with that you will form what? Along with that you will form pyridine picks up the proton, right? So we have nitrogen used its lone pair to attack the positively charged hydrogen. So NH bond will be present. So nitrogen will have a positive charge. This is nothing but your pyridinium salt. So now whatever we get CH3, CH2, CH2O, S double bond of Cl, and we have chloride ion in the reaction mixture. The chloride ion in the reaction mixture is not supposed to pick up the proton because proton is already picked up by the base pyridine. So now chloride ion will do what? It has no other chance. It has to attack this electrophilic carbon only. Yes or no? In which way it will attack? CH3, CH2, CH2, oxygen with two lone pairs, S double bond of Cl. Now we have chloride ion. Chloride ion has no proton to pick up now. So Cl minus has to attack this particular carbon in the SN2 manner. No other chance. As soon as this attack occurs, this CO electron density will be given and sulfur chlorine bond is lost. We will form CH3, CH2, CH2, Cl plus S double bond O, S double bond O plus a Cl minus. This Cl minus and pyridine, whatever you have, will have electrostatic force of attractions. Like pyridinium chloride is going to form. Right? So what happens in this case? Now you can answer. Inversion or assimilation or retention or both A and C. I have given the complete mechanism, students. In this reaction, what happened to the stereochemistry of the product? It will be inverted or assimilation or retention or both A and C. What happened? SN1 occurred or SN2 occurred or SNA occurred? SN2 occurred or not? Cl minus attack this electrophilic carbon from the back side. Yes or no? SN2 means what will the product?
Inversion product.
Inversion product. Okay. So you have to understand this point carefully. Whenever you are treating with thionyl chloride, alcohol with thionyl chloride, in the presence of pyridine, SN2 attack. In the absence of pyridine, SNI attack. SN2 attack means inversion. SNI means retention. So A will be the right answer. Okay.
Yes,
So,
sir.
right. Very good. These are about your nucleophilic substitution reactions, SN1, SN2, and SNI. So after that, we can also discuss what is the next type of substitution. Electrophilic substitution reactions. Addition reactions are three types. Electrophilic addition, nucleophilic addition, free radical addition. Substitution also 3 types. Electrophilic substitution, nucleophilic substitution, and free radical substitution. Nucleophilic substitution we have discussed SN1, SN2, SNI. Electrophilic substitution we are going to discuss now. Electrophilic substitution reactions. So we can say this as ESR, electrophilic substitution reactions. Now take a which type of compounds will be undergoing electrophilic substitution reactions is mostly benzene and derivatives of benzene. Because of the electron rich, because of the pi electron density present on the benzene, the CH bond can be replaced by any electrophile. Okay, write down that point. The electron rich benzene can undergo electrophilic substitution reactions. The electron rich benzene can undergo electrophilic substitution reactions. In these type of reactions, step 1 is, in these type of reactions we will have 2 steps majorly. One step is the formation of electrophile, second step is the attack of the pi electron density of the benzene or derivative of benzene on the electrophile. In these reactions, first step will be generally will be formation of electrophile. In these reactions, first step generally will be formation of electrophile, and then the attack of pi electron density of benzene occurs to form substituted product. Very simple reactions. So we have 2 cases. If you have benzene and derivative of benzene. If you have benzene, it's fine. If you have a derivative of benzene where electron donating group is connected, like let us say electron donating group like OH is connected. If you try to write the resonating structures, lone pair of electrons and oxygen comes into, pi electron density moves away. So electron donating groups, either by inductive effect, either by mesomeric effect or by hyperconjugation, they will generate what type of charge at ortho and para positions? Negative charge. That means electron donating groups increase the electron density at ortho and para positions. So negative charge comes into the C double bond C, pi electron density moves away. So negative charge will present here. Carbon carbon double bond, C double bond O, one lone pair OH bond, positive charge. Negative charge comes into, pi electron density moves away. Negative charge presented here. C double bond O, one lone pair OH bond, positive charge. Negative charge comes into, C double bond O, pi electron density moves away. So we have double bond here, and OH oxygen will regain its lone pair. So electron donating groups increases the electron density as electron density at ortho and para positions. So electron donating groups are ortho para directors. They direct the electrophile at the ortho and para positions. So electron donating groups are ortho para directors, ortho para directing groups. If you have electron withdrawing group withdraw the electron density, thereby developing what charge at ortho and para positions? Withdraw the electron density, forming C double bond C O minus OH. We have double bonds like this. Again, you try to involve that into resonance. Positive charge, double bond C O minus CH. Again, positive charge, double bond C O minus CH. Again, negative charge comes into, C double bond C, pi electron density moves away. So they actually decrease the electron density or not? Electron withdrawing groups decrease the electron density decrease the electron density at ortho and para. Electron density at ortho and para, and meta is electron rich comparatively. Meta is electron rich comparatively. So they are meta directing. They are meta directing. Is that clear, students? Understood these points or not? So reactivity order, which is more reactive? Electron donating groups. It doesn't matter how weak electron donating group it is. The weakest electron donating group will also have more reactivity when compared to the electron withdrawing groups. So if you try to look at the attack, electron donating groups will be always having greater rate when compared to no substitution, and they will be having greater rate when compared to electron withdrawing groups. Rate towards electrophilic substitution reactions. And electron donating groups. What are the electron donating groups? You can think of OH, CH2 minus, O minus, NH minus, NH, C double bond or CH3 with a lone pair of electrons on nitrogen, NH2 with a lone pair of electrons on nitrogen. All these are electron donating group. Electron withdrawing groups, CH2 plus, C double bond OH, C double bond OH, yes or no, etc. And one major drawback or the misconception which we comes here is alkyl halides, aryl halides. That you have to write aryl halides, okay, or haloarenes are electron withdrawing or electron donating. We all know for haloarenes, the inductive effect is dominant when compared to the inductive effect is dominant. That is, electron withdrawing tendency is dominant when compared to electron donation by mesomeric. So they are ortho para directing or meta directing. Haloarenes are ortho para directing only because electron donation is happening from the lone pair of electron chlorine, or ortho para directing groups, but they have less reactivity when compared to benzene. But they have lesser reactivity when compared to benzene. Understand these points carefully. So whenever you're comparing the rate of electrophilic substitution reaction for benzene and halo compound, like benzene and chlorobenzene, let us say, benzene will undergo greater electrophilic substitution reaction. The electrophilic substitution reaction of benzene is higher. The rate of electrophilic substitution reaction for benzene is high when compared to the chlorobenzene. That is the first point, because chlorine is actually withdrawing the electron density from the benzene group as a whole. But if you think of the substitution happening at what positions, it will happen at ortho and para only. Generally, ortho para substitution should be having greater rate when compared to benzene. But here in the halogen compounds like haloarenes are ortho para directing group, but they have less reactivity when compared to benzene. So you can compare electrophilic substitution reaction rate is greater for benzene when compared to halobenzene. But halobenzene is ortho para directing, but chlorobenzene is ortho para directing group. Is everything clear, students, so far?
Yes.
Yes or no? What are the different reactions where you can understand this electrophilic substitution happening? Electrophilic substitution reaction or happens like Friedel-Crafts alkylation, Friedel-Crafts acylation. One day I have discussed about FeCl3. Like whenever you have Friedel-Crafts alkylation happening with the alkyl halide like this, do this reaction. Like I have taken benzene and I am treating this with CH3, CH2, CH2Cl in the presence of AlCl3, and same benzene treated with CH3, CH2, CH2Cl in the presence of FeCl3. This example I have explained earlier. How many of you remembered?
Yes.
Yes, Fatima. So what happens? In the first case, what happens? The carbon chlorine bond is going to be cleaved. So we'll get this type of products. You get CH2, CH2, CH3 here. Whereas here you will be getting CH, CH3 and CH3. So what will happen? Mechanistic approach will understand now. Mechanism and reason. So first you have CH3, CH2, CH2, Cl treated with AlCl3. AlCl3 will act as a Lewis acid. Carbon chlorine bond will leave. So carbon chlorine electron density will be given to aluminium, generating CH3, CH2, CH2 plus and AlCl4 minus and AlCl4 minus. And then we have respective benzene. The pi electron density of benzene is going to be attacking respective carbocation, but since carbocation is formed, rearrangements are possible. So 1, 2 hydrate shift occurs to form a secondary carbocation, CH3, CH, CH3. So we have written reverse, I think. Okay, in the AlCl3 we'll be having CH, CH3, CH3, whereas in the FeCl3 we have CH2, CH2, CH3. That means rearrangements will happen in the presence of AlCl3 because AlCl3 is a good Lewis acid. So carbon chlorine bond cleaves, carbocation is obtained. So the pi electron density will attack the carbocation to form this type of species, CH, CH3 and CH3. Now we have AlCl4 minus in the reaction mixture. This AlCl4 minus, it is nothing but sigma complex or Wieland complex. Initially we have aromatic nature for benzene, but as soon as this complex is formed, it is stabilized just by resonance but no aromaticity. To regain back the aromaticity, AlCl4 minus, which is present in the reaction mixture, that picks up the proton, CH electron density comes into to form respective compound like this, isopropyl benzene, and HCl plus AlCl3 is released back. In case of FeCl3, the formation of FeCl4 minus will not happen. SN2 attack occurs. Like SN2 attack, why I am saying? SN2 attack of pi electron density occurs first on alkyl halide, which generates FeCl4 minus. Because FeCl3 is a weak Lewis acid when compared to LCl3. This is because FeCl3 is a weak Lewis acid when compared to AlCl3. Everyone got this or not?
Yes, sir.
Yes.
Yes, right. And now I have taken benzene treated with the CH3, CH2, CH2Cl forms a respect to sigma complex, which will again undergo isopropyl benzene. Isopropyl benzene I'll treat with O2 in the presence of H mu. This I'll treat with O2 in the presence of H mu first step. Second step, H plus in the presence of H2O. What happens? What is the product?
Phenol.
Phenol. Yes or no? From the cumene we will generate respect to phenol. The mechanism of this reaction we'll discuss. This is an industrial method of preparation of phenol. Industrial method of preparation. Of phenol. Okay. Is everything clear, students, so far?
Yes, sir.
Okay. Next class we'll discuss about Fieldcraft's alkylation, acylation, and nitration, sulfonation, everything. Then we can proceed with the different other reactions like free radical substitutions, then elimination reactions. Right? I'm explaining all these reactions with mechanism so that you can understand and apply these concepts whenever I'm discussing particular organic chemistry chapter. Like after this, we'll discuss haloalkanes, hydrocarbons, alcohols, phenols, ethers. You have to answer all the questions over there. Whatever the type of reaction I'm discussing, it will be falling under these categories only. You should be answering. Okay, and you might be feeling a little bit difficulty in the initial phase, because mechanisms might be little bit lengthy, but you don't think like that. Understand them clearly. If you have any doubts, you are free to ask. Fine. Thank you all, everyone. Bye.
Thank you, sir.
Thank you. Thank you so much.